Hi everybody. Today we have our Diana topical meeting, and we mostly will be talking about the ROOT IPCC, which is going to be presented by me, and the next presentation is going to be done by Raphael about the C++ modules. So both of those developments are being done in the context of the ROOT project. So this showcase presentation is essentially the presentation or a version of the presentation that we're going to show to Intel as part of the IPCC showcase presentation request. Some of the data that I'm going to show is preliminary because we are constantly doing benchmarks and and trying to make things stable so that we have like a stable results and nice plots. And yeah, so let's go on the next slide. If I can change it, yeah, I need to click. So what is Intel IPCC-ROOT? So very quickly, it is a Princeton Intel Parallel Computing Center to modernize ROOT funded by the Intel Parallel Computing Center program. So it started, so the grant was approved, I think 2016, but the work started in 2017 in coordination with CERN Open Lab. And currently it's only one full-time engineer employed for one and eventually one more year, and that's me, and I'm located at CERN. So our work plan for 2017 was to basically perform 3 different tasks, mostly in math and I/O. So the first task was to integrate and help with the ongoing vectorization work in ROOT. The second task that I'm going to present a little bit today was to integrate a new way of differentiation based on the so-called automatic differentiation techniques in ROOT. This is going to be especially useful for minimization and fitting algorithms, where we hope that it would improve things a lot. And the third task was the thread-based file merging feature, which was originally developed by Vitek in the context of G and V, where he wanted to merge and to have like multiple threads writing to file, but only one file on disk. The idea here is to port this to ROOT and follow the ROOT coding convention standards and try to find out what are the performance bottleneck of this kind of approach. So as you can see, the plan is very concise and very one can think minimalistic, but we want to be very clear on what we want to achieve and what we want and what we can deliver. So the first step was to help a little bit with the vectorization efforts in the ROOT team. What's the current state? We have basically one library, which is sort of standard, becoming standard for VecGeom and G and V. And this is VecCore. It is a SIMD vectorization library which wraps VC and UME SIMD and provides a uniform way to access functionality and facilities from those 2 libraries. And as I said before, it is used in G and V extensively, and this was also subsidized by the Intel G and V IPCC initiative.
I have a correction to make.
Sure, go ahead.
It's just formalities. So there were 2 IPCCs, one G and V CERN, and the other one is UNESP.
Okay.
And VecCore was basically entirely developed by the UNESP IPCC.
Okay.
So if you can please make that correction.
Sure. That was okay. I will do that. So yeah, thanks for the comment. I wasn't aware of this. So as of now, the core can be enabled in root by passing -d built-in the core equals on, and you essentially ask root to turn its own explicit vectorization capabilities. So the first step that we embarked on, I personally embarked on with the vectorization in root, was reviewing one of the major pull requests that we had from LHCb of vectorization of the GenVector math library. So the contribution was fairly well defined and fairly well developed, but it required quite some iterations from the root team to fit our coding standards and some of the things that weren't clear to be cleared out. And here, to be clear, this work started before integrating the core. So the only way we can proceed with the vectorization at that moment was to employ VC. So it is based on the VC, which is essentially easy to change and use the core there. And as I said, after many iterations and improvements, this landed in the latest release of root, which is 6.10. Some benchmarks of GenVector. We have one significant benchmark, which, from what I understand, matches more or less the LHCb use case. And this is a simple ray tracer, which is very heavily using the GenVector operations. And the benchmark essentially compares the vectorized versus scalar mode of ray tracing photons, and at the same time it's checking the result correctness, because with vectorization we have the challenge to ensure the correctness of even some of the basic functions that we take it for granted. Whereas if you have them vectorized, it's not quite clear, or it's not obvious that they would produce the same results. So that work is extremely tricky, and at least me personally, I'm insisting on extensive correctness checks, because we have seen cases where correctness is just lost, and then out of a sudden vectorization and performance loses any meaning if you cannot produce correct results. So the test bed of this particular benchmark is the following, and you can see the same pattern as in the rest of the benchmarks in this presentation. So we benchmark two compilers. This is GCC 6.2 and ICC 17, and we check and we test on platforms which are Xeons and KNL machines. I can disclose the precise models of those machines upon request. And we test in two modes: SSE mode, which is widespread, and every laptop or every device which is on the market essentially has it, and AVX2, which is only available in some server class or some more advanced devices. And also we test on KNL, which is the newest PCI card that's coming up from Intel. And you can see that on the x-axis we also have the amount of photons, so the amount of work that we have been doing. So we start with 9.6 K, that would mean 9,600 photons, and then we go to around 96,000, or no, 9,600,000 photons. And you can see here the benchmark results. We see a little bit of a performance degradation when we go to doing more work, and this is because of probably some memory operations that are done, which are sort of being shown here in the benchmarks. Overall, the results are pretty consistent. They vary from 1.8 up to or 1.7 up to 3 something. In some cases, I would expect some further improvements, but this needs to be investigated a little bit more with some tools and profiling. So those are the preliminary results of this very big gen vector test.
And this is single-threaded, right?
Yeah, this is single-threaded, so no threads, no nothing here. Just plain vectorization. So the next thing that I wanted to see and wanted to investigate is which are the bottlenecks or where the implementation doesn't vectorize well. So for this, I was doing some investigation, and I found out that micro benchmarking could help us there. Micro benchmarking means that we have like unit tests. So we benchmark certain atomic functionality. Say you have a class and you have a methods in that class. A micro benchmark would be to stress a certain method of the class. And surprisingly to me, the simple ray tracer scalability looked almost perfect for, at least for the ACC example. There were a few places where I hit almost straight away when I started implementing the micro benchmarks. One of those places is deep in the Cartesian 3D coordinate system, where we had to compute the angle of theta, but this would be become more clear in the next couple of slides. So the other interesting thing, which made me believe that the micro benchmarking is the also a complementary way of reasoning about performance, is that when I started doing it, from what it seems a very reasonable pull request and a very nice contributions from the outside, when I started micro benchmarking, it turned out that some of the changes, they did not compile in vector mode, so they could not even take vector types, even though they worked very nicely in the overall example. So the impact of the work here is that LHCb uses the gen vector library from the rich mirror system, and you can see here on the right-hand side that the work was presented on by Chris Jones. So this is this work originated from Chris Jones from LHCb, and he presented this and the improvements of the vectorized gen vector library in one of the LHCb software weeks, where he reported nice improvements. The next thing in the vectorization that I've been not so involved was the vectorization of the fitting mathematical library in Root. This was conducted mostly by Xavi, a fellow Root team member. So his work was to start vectorization of bint and bint likelihood functions in the fitting, and some improvements or some work already landed in the last release, which was 6.10. So there you can see the performance of the unbint likelihood function log L. From the synthetic tests, we see depending on the version. For GCC, we get 1.662 or similar results, and then there is a spike which needs to be understood for AVX2 and GCC 6.2. We get around 6 times faster vectorized code on KNL than the scalar code, which to me is a little bit of a surprise, given the fact that we with ICC we get something like 2.8. Another interesting point of the benchmark, yes, you want to say something?
Yeah, that is a bit surprising. I wonder what flags you use to compile the code.
Nothing special from the ICC compiler. For GCC, it's the
architecture flag.
No, the architecture flag is the default that we compile right now. I don't know what.
How do you switch between SSC and AVX2?
Oh, no.
Doing
native. I do an MARC native. So for both cases, I do.
Oh, you do MARC native.
Yeah. For the one that I'm saying AVX, so for AVX2, for ICC 17, I'm passing like MARC native. and also for the GCC version and pass on to American Native. So they should be the same.
If you do American Native, it will enable AVX512.
For the KNL.
For both. Yeah, for the KNL. Yeah, for the KNL. It
Yeah.
will enable AVX512. If you use VC, it may only use AVX2. But
no, here we're using, I think, for the logL, we're using the VecCore.
Oh, okay, but VecCore with what backend?
I think it's the default, is the VC backend.
Okay, yeah, because VC doesn't support AVX512.
Yeah, this is a surprising result to me. And if you look at the results from the SEC with ICC-17 for the Xeons and not for the KNLs, you see 1.04, which I find very surprising as well.
Yes, I think VC has a problem with ICC. It may have been the version you used. If you use the very latest version of VC, you probably will avoid this problem.
Yeah.
And it may depend also on the version of ICC. I know that there was a problem. We reported it to both Matthias and Intel, and it took a while, but eventually it was resolved.
Yeah.
And since VC doesn't support AVX512, we may have a good result by using the scalar implementation, which is a fake vector. But the ICC vectorized that quite well.
Yeah. Okay. Yeah. So I guess what I'm saying, or what I can conclude, is that we need a deeper investigation of those results, and probably I need to run some more benchmarking on it with some more flags. I'm pretty sure that the flags that I'm passing to GCC and ICC are the same, but I need to double check. The next step here would be to start implementing micro benchmarks so that we can have more focused approach towards the vectorization of the fitting libraries, and there we expect to get more answers, which is the bottleneck.
There's another comment. You may be seeing bad speedups with ICC because the scalar code is fast.
Yeah. This is.
Did you look at the time also instead of just the speedup?
Yes, for this one I'm looking at the time as well. So the time is it's the one that has like almost 6 times improvement. The one runs for 4 seconds. Mm-hmm. The vectorized code runs for 4 seconds. The scalar code runs for 26. So it's.
And what about the ICC?
This is the ICC. This is the 6.84 that I'm talking about on KNL.
No, that says GCC 6.2.
Ah, yeah, you're right. Yes.
So this speed up is scalar of GCC versus vector
of GCC. Yeah.
Sorry, I don't want to interrupt.
No. This is interesting.
Because if ICC is vectorizing your scalar code, of course the speed up is going to be bad, right?
Yeah.
Like SSC 1.04. Maybe your scalar code already has SSC in it. That's what I'm wondering.
Yeah, this needs to be checked. Note taken. So let's skip. So we're going to the our actually third item on the working plan, which comes second, and I will tell you why. So this is the thread-based file merging in root. So we want to enable a very simple paradigm of expressing code, and this we want to have a single on disk file while we could write from multiple threads on it. And we want to give the user the ability to express this in a transparent way, so that the merging of the multiple writing is happening with a worker thread, and it's only writing on one file on disk. Currently in root, we have the ability to write multiple files from different threads, but they have different output files on disk. I'm missing a slide here. I don't know what happened, but so essentially we have put that for the last quarter of this year as implementation, but the root team assessed that this is an important ingredient for the root project, and we decided to put it in 6.10. And this was done with in collaboration with the root team, and mostly work was done mostly by Guilherme, who did the majority of the changes and the porting of the GNV prototype to root, and essentially ending up rewriting it.
Yeah.
But so from here you can see this is going to be turned into a nice plot. But here you can see that those are the micro benchmarks that I've been talking about, and here we fill a T3 with random data, and we flush we flush to disk when the data in those multiple files becomes more than 32 megabytes. And you can see here on a machine where it has like 4 cores, which is my laptop, how it scales. It scales well up to 4 threads, which is the count of hardware threads I have on my laptop, and then it gives some good results on with hyper-threading, and then going with more threads, we do more work, and we eventually degrade the performance. So this is something that we need to investigate a little bit more, and there were some pull requests opened to reduce the effect of the fact that we don't have thread-safe reflection information backend in root. And this is something that we found out. We knew, but we found out, and it becomes more and more important for us in order to be able to work with multiple threads and threading in general in root. So as I said, it was scheduled for the last quarter, but the root team assessed that this is something that they want now, and we started working on it. So the impact is that CMS is having a use case where they want to write multiple files in multiple threads, and they see some stalls because of this missing concept, and they ended up implementing this based on the same internal infrastructure like tmem files, and they are looking forward, and this was presented a couple of times, and the last time was presented on the root workshop, root IO workshop by Dan Riley, that they are looking into this, and they're very interested in seeing progress in this direction. And I think it was a good move to have it in 6.10 so that CMS can have their hands on and start playing on it, and hopefully solve some of the problems that they have in the IO. Another use case, which was actually the driving the schedule of this feature, was the new analysis infrastructure, which is called T-Data-Frame in root, and it's based on the functional programming paradigm, where you express things and computations in a different way, more functional, and this gives the chance to the implementation to decide whether it wants multiple threads or to do something smart behind. And you can see here that this work was presented by Guilherme, Danilo, and the rest of the root team at the Root IO workshop, which took place a couple of months ago. And here you can see that this is one of the first data that we managed to take with the parallel file merging class, and it was not so good. So we went back and we had to figure out what were the problems, why we don't scale well, and this was mostly the locking and the non-thread safe reflection backend that we have in root. This has been worked on, and we hope to see improvement there. I think we have some improvement already, and those slides are a little bit outdated, but this is the last thing that was presented, and this is the last thing that we have in the last release. So moving on, this is something that I would like to present, even though it's not completed. This is a work in progress, and this is the so-called automatic differentiation prototype, which has a name CLAD in root. So this is a library that I started in 2014, and now we want to use it in root when computing derivatives. So the way that it works is that we have a plan to get this library. It's sort of in a prototype phase, but it works. It has been tested. It produces the proper derivatives, and then they're computable and they're fast to execute. So the plan there is to enable the use of the library in root by connecting it to its interpreter, which is also based on Clang and LLVM. We need to make some updates of the code because it uses some of the Clang internals and things change among the versions. And we need to integrate the automatic differentiation into some non-trivial examples in Minuit 2 probably, and TMVA for multivariate analysis, for example. And like a final step, we want to benchmark those and show improvements. So one very quick summary of how the automatic differentiation tools work is that the cloud library, there are two modes in trying to produce a derivative. One is the numerical one, where you have a normal Newtonian method where you have iterations and converging towards the value of the derivative. And there is a symbolic mathematic approach to it, where the symbolic approach is slow in most of the cases, and in the numerical differentiation is inaccurate because of this iteration. You have to deal with most of the time floating points, and then you have accuracy problems or you have convergence problems. Sometimes the algorithm cannot even converge. So the automatic differentiation techniques are basically defining out those problems by introducing extra software dependencies. That is, it considers that every computer program can be divided into a set of elementary operations like subtraction, addition, multiplication, division, and atomic functions like sinus, cosinus, logarithm, and others. And by applying gradually the chain rule of differentiation, we can produce a mathematically correct derivatives for arbitrary order, and then we can compute them in a very efficient way as at the cost of a function pointer. So consider the example below. We have some function which computes power of 2, and we piping it through this or any differentiation tool out there, you get something like my power second. So essentially a derivative, which is a second function, which is similar to the one before, but also following the derivative, the derivation rules. In my case, we're using CLAT, I get my power underscore derived with respect to argument 0, because we have only one argument. And then you can see that in the right-hand side, the x squared becomes like 2x. And this is basically the principle of every other mathematical derivative computation of this tool. So some of the advantages here are compared in code, which you can actually run and test. So some of the comparison is here. I have naively implemented a numerical differentiator, which computes the value of the derivative using the finite differences approach. It's very simple. It takes a function, it takes a value, and it takes a step, and it takes an error, and then we iterate until we have achieved the conversion step, and we get a value out of this. And here is the other example that's produced by an automatic differentiation library. In this case, it's CLAD. You can see here that the production looks very closely to what you would write by hand. And this has a lot of advantages because it avoids the precision losses on the next slide. Here on the left-hand side, you can see that even for the numerical computations, even for something very simple, like comparing my sinus of 30 and for equality to my cosinus of 30, it yields precision losses. And from basic math, we know that the derivative of a sinus x is a cosinus of x. And in principle, this should hold. You can, if you say derive my sinus and pass an argument like 30, it should be equal to my cosinus of 30. This is basic from the basic mathematical rules. But if you compute the values with the numerical differentiation, you get a precision loss. And this program on the left-hand side would have an output that there is a precision loss there. And on the right-hand side, you can see that there is no such a thing when we compute the same derivative with the automatic differentiation techniques. And also, you can compare instructions. Of course, in this tiny program, the instructions that it takes to compute a value are far more difficult to optimize rather than the instructions that you get from the right-hand side, where everything is pretty obvious to the compiler, and the compiler can actually perform much more optimizations and even apply some implicit vectorization there. So this is more or less the next item that needs to be done, and I will be focusing on. And for further reading about the automatic differentiation, there are a few sources and about PLAT, and also there's a dedicated site on this technique, which is called autodiff.org. You can go there and visit to see what are the other products out there. And while working on these few things, there is some extra work that was conducted, which has relevance. What we have done recently, and also thanks to Guilherme that he was fixing a few issues, we were able to restore the nightly builds of root and ICC-17. So we build root on a regular basis with ICC-17. We now use O2 as optimization level for root release builds by default when building with ICC. It surprisingly to me, it was set to O0 for some reason. And since I think 2009, we have been building with O0 when doing release plus asserts mode.
It could be funny floating point behavior.
Yeah, could be, but
we can set to be IEEE compatible, and then we can enable optimization.
Yeah, but I haven't seen failures though.
No, I haven't either, but we should probably still add.
So we keep it running.
Avoid unsafe.
Fast
math, because I think the thing with ICC is that it enables fast math by default, and fast math is not really that safe. So we probably want the optimizations like loop, vectorization, whatever, but we don't want ICC to go around and change our associativity, this sort of thing that can break code.
Yeah, definitely. I'm not sure, but I have seen in the CMake that we are adding some flags. So maybe this is already the case, but I need to double check. We'll see. So what we did is after the LLVM upgrade, we enabled the optimization passes for runtime code. So the interpreter runs in O2 mode. And from the preliminary stress tests, it's not quite clear whether this is an improvement or not. But I think we need to decide on that. In the meanwhile, I've also enabled some tools ensuring contribution quality, such as Clang format, Clang tidy, static analysis check, Clang tidy modernization checks, and so on. So here the idea is to be able to aid external contributions, either vectorization or any other part of root where we can diagnose certain problems with the code before actually looking at it, which is very useful. It found out quite a few issues, especially the Clang tidy tool. And we have reported and fixed a few build system issues, most notably the when building in massively parallel mode in kernel. Here, Raphael helped quite a lot, and some other stuff that are. So this is probably outdated now with the recent fixes, but this is how the the root builds look like on massively parallel machine. Here we build with Mana J48. And we see that there is some bottlenecks here and there. Mostly from what I have seen is it takes quite a long time for our dictionary or our reflection generator to generate data. So maybe we should look at this one so that we can further parallelize and optimize the build.
Still, with 70 threads, I compile root in 5.5 minutes.
Yeah. So it is good, but there are some bottlenecks that we need to iron out, I think, as well. And yeah, that's the button. So other potential investigation targets for optimization. This is the continuous integration of these micro benchmarks. We want to make sure that we don't regress in performance. Once you do it, we want to make sure that we don't have to do it in 2 years from now, or 1 year from now, or 1 commit from now even. We also are thinking to enable the default architecture in the root C++ interpreter to the native one.
I think that's dangerous.
We need
if you're distributing over CDMFS, that's asking for trouble, because then you will enable the thing of where you built it, and then people are going to log into LX Plus where these old machines don't have the instructions, and they're going to have failure.
This is the interpreter when it starts up. So we don't ship anything, we compile in memory. So in principle, we define away this problem. It's not computation, it's the runtime. So whenever it starts, you get this MR.
So the stuff they compile after you run the interpreter, but the compiled version that people load, root, will not use those instructions.
Yeah.
And are we sure that that won't create,
This needs to be checked. This needs to be checked. I assume that if we enable this, we will get much better instructions for vectorization, and we have sort of good continuous integration system where we can detect these cases. If it's something very obvious, we should be able to see it in the bots. And last but not least, it's the C++ modules, and I'm here referring to Raphael's talk. And I think this is pretty much it on my end. Sorry for taking too long. I just want to say thank you, and thank you to Guilherme, Oksana, and Raphael for bearing with me most of the time and helping with many things.
Yeah, Raphael did great work on the new system.
So I think we are collaborating pretty good, and I really appreciate it. So yeah.
By the way, the experiments already run MR on their dictionaries, their compiled ones, but the interpreter is not using MR. So we already kind of tested this is not. Like it can create funny conflicts because we have different defines if you have MR. So you can test for SSA, but it doesn't seem to.
Yeah, we tested the other way around. Right?
Yeah.
The other way around is fine, because if the interpreter is never calling vectorized code from the library, even though the library has it, it's no big deal. But if the library doesn't have it, and then you try to call vectorized code, then you may have a problem.
Yeah, and also it's that we probably don't have a lot of vectorized code. I don't know.
The instructions by themselves are not a problem. The problem is if you try to call something that depends on vectorization, and then you compile the thing that you're trying to call without vectorization, then you can have a problem. But it's only at the function call. The instructions by themselves should
but this should be very visible because it's immediately an ABI issue. You just see a crash. It's not like a subtle something that gives you the wrong result out of a sudden, which is what I'm most aware of with vectorization stuff.
Okay,
which is most afraid of.
Let's get some models because we really rate already.
Just wanted to say, remote, do you have questions? Probably I bored a lot of people.
Questions to me.
Sorry, yes?
I said no questions from me. Thanks.
Oh, okay. So, Raphael?
Yeah, this doesn't work. Let me check.
I know the magic combination.
Good. Cool. Yeah. Okay, hi. Welcome to the root C++ modules talk. So this is about moving or making root use C++ modules and getting CMSSW using C++ modules. And this is by me and Vassil, this like cooperation work. Okay, so what are C++ modules, or also called PCMs? So modules are nothing more than a system to more efficiently load like a library you want to use. So you have like a library, it has a header, and you want to bring this header into your translation unit or into an interpreter, and what usually happens is you just go into the file and you start parsing it, and then you add all the AST nodes to your translation unit. And what modules are doing is they kind of work around the parsing process that we usually do. It's really similar to the way we already handle the root headers. So the root headers are compiled into a PCH, which is really similar to PCM on a technological level. So it's the same code actually in most parts. But the problem is with the PCH, and this is why we can't just use the PCH for everything, why we need modules is PCH is only one, and modules are like a PCH, but you can have multiple, and you can attach multiple PCMs like a PCH to your compiler, and then a compiler can use them to load headers instead of parsing them. And so C++ modules, you probably already heard this in another context, which is like an extension to the next C++ standard, hopefully. And it's not necessarily developed by us, it's like mostly developed by Google and Apple, which implement or have one implementation in the Clang parser. And their motivation is mostly to get their compilation times down, because they spend a lot of time reparsing the headers. If they have one header and they use it 100 times, they parse it 100 times. And the idea with modules is that we just parse it once, we serialize it once in a format, and then start loading from this header. So we save all the parsing times and only have a really small deserialization times. Yeah, and they collaborate with us. So we have regular meetings with them, and they review our patches and get them into Clang, because Root is using Clang. So we more or less get all their work for free, because we just hook up in the work they're doing for making modules work, and we just use them in our Root interpreter. And yeah, the code is open source, so it's like Clang, it's an open source part of Clang. It's not like some commercial extension. Yeah, and our motivation is not we don't want to bring down compilation times. Our motivation is actually getting down runtime, because we are running an interpreter, Cling, which is based on Clang, and which at the moment has to parse headers at runtime, and we want to prevent this and want to, instead of parsing headers at the runtime, want to just deserialize headers from a C++ module. Yeah, so here's an example, or not, wrong thing. So here's an example how this usually looks like. We want to use a certain class, for example, my lib class float, and my lib class float is somewhere defined in some header, and we have some mapping between a class and a header we want to use. So if you start using a certain class, the interpreter parses the certain header that the class is defined in to get a definition in the methods that we need to call. And this is currently taking time of the runtime, because during runtime we start parsing these headers. This means that if you include a header, you actually waste runtime, because you spend time on parsing the header. Yeah. So let's see what modules can do. So we have two examples how we want to profile modules, or give like some first performance results on how modules work. Because modules are not ready at the moment in the root interpreter, but they're ready in Clang, more or less. We make the profiling based on how Clang works, because the Clang parser is the same as the root parser for the biggest parts. So if the Clang parser is faster and using less memory than the root parser, which is the same code, is using less memory and is faster. So in the first example, we include 4 headers, and we instantiate from each header a class. And we mostly want to force Clang to actually start using the headers. So it's not just we want to include them, but we also actually include them for a reason. So Clang can just optimize and say, no, there's an include, but he doesn't use it, let's ignore it. So we take a header, we use it. This is the first example. And the second example is more or less what the interpreter is doing. So what we see on the left side is the way how the interpreter currently works. It has some forward declarations, and we give them an attribute, and the attribute tells us what header do we need to include if we use this class. So if you use tf-plot reachL like we do here, then the interpreter automatically includes this. So this is what we simulate with the file on the left side. We have the forward declarations, which consumes the memory. We use the tf-plot treat_dgl, and we instantiate an object there, and this forces the interpreter to include something. And we just pack this in a file and compile it to get some performance measurements. And on the right side, we do the module case, and the module case is, as you can see, a bit more extreme. So we include everything. We don't make any forward declarations. And yeah, and we also use the same class. So we have the same code. We have the same semantics behind. and we also include the header. So here we include everything. Here we only have forward declarations and include only the specific header we need for our class. And we want to see how those two compare. So the left side is without modules, and this is how we work with modules. So let's take a look at the memory that we use. So we have 3 bars here. The left side is always for the first example. This was the one where we just include 3 headers and use them. And the right side was the one we just saw, where we have 2 different kind of codes for this example, where we simulate interpreter. So on the left side, you can see we have 1 bar, which is the big one, which is without modules. So this is the size of the AST Clang generates for this code. So this is all the parsing. We get all the declarations, all the statements, and we consume around 32 megabytes. When we use modules, Clang modules, instead of parsing the header, we only serialize the stuff we need from the specific headers, which saves us around 10 megabytes. And then we have another bar, which is the green one, which are patched modules, which is some performance optimization we're currently testing, which we hopefully see in practice soon. And this is taking another 10 megabytes off. So just for the curious, the performance optimization is mostly that currently template and template specializations are not very well handled in modules. So we made like some small optimization there, which actually gives us a lot of memory off. So what we see here in total is that from moving from non-using modules to a Clang parser that is actually using modules to use headers, in this example, we actually save half the memory. On the right side, we see our interpreter code where we already optimized for ensuring that we are not including anything that we don't necessarily need in the non-modules case. So in this case, we're more or less even. So we include, so on the left side, we just include the TE3D-GL header. And on the right side, we include all headers that we have in the library. And we have the same memory. So for modules, including headers, practically free if you don't use it. And here we're more or less the same size, mostly because of the missing optimization. And on the right side, on the green header, we see actually what happens if we start our optimization there. So even in a case where we ignore all our optimizations we currently have to prevent unnecessary includes, modules are more or less performing the same. So they more or less make all our current manual efforts to prevent including stuff obsolete, but just automatically preventing unnecessary includes from affecting our memory. Okay, so now let's take a look at the speed. So here's the speed, the same examples. This is the parse time. So this is the time between opening the file and actually having a complete AST that we need to compile this into LLVM module. So on the right side, we have without modules, we take around 3.3 seconds. And then we have with modules code, and the with modules code is much, much faster. I think this is like 10 times if I remember correctly. And the main reason here is we save the complete parsing process. We don't have a lexer, we don't have a parser that goes recursively through the AST and starts creating nodes. We literally just load the nodes from the C++ module, which is a binary file, which is really optimized to use the same data structures we use in Clang internally. So it's just loading, just creating an allocation and just filling out the fields. Yeah, and again, our optimization is cutting this in half. So on the right side, we are in the interpreter case. We take around 1.7 seconds without modules, and with modules, again, we're losing like a tenth or something. Or we're using a tenth of the time, and the patch, again, cuts this in half. So this is the kind of optimizations we are aiming for in terms of speed, in terms of memory for the interpreter when we move it to use C++ modules. Another example is here we compile root with modules. So we just enable C++ modules in Clang, and then we use Clang to compile root. So then Clang just uses the modules we currently use, we want to use during runtime, actually just to compile a code in each CXX file. And here we see the 2 bars for each package. So on the left side it's always with modules, and the right side it's without modules. And usually it goes by half. There's one exception, this is core. And the main reason is that CMake is not very well optimized to build on modules at the start. So the modules are built on demand. So if you include a header on the first time, it starts building the specific module, and this goes recursively on. What actually should happen is that CMake sees, okay, we have 10 modules and then splits them up on 10 threads. But what actually happens in this case is that one thread compiles at the start all modules. So in this case, we're actually slower, because if you use 7 threads, then 6 threads are doing nothing while the modules compile, and so we have a lot of wall time here. So this is not CPU time. This is just one thread compiling on modules, and then the rest of the wall time here is just the other threads waiting on the modules. Whoa. But this is just a limitation of the build system. Yeah. Okay, so if you want to remove root and CMSW to modules, we have around 6 points that we want to work through. The first one is we want to compile root headers into C++ modules. So the motivation for this is that C++ modules are like still a work in progress, and we want to test if they work on our code base. And it's easier to debug if you just compile, if you use them in the way they're intended to compile code, and just use the same headers that we would use during runtime. So if we run into problems, we can just reduce the file example and don't have to mess with the interpreter that is adding includes, because Clang is like a more minimal version, easier to debug. The second step is more or less the same that we have in the first one, which is compiling all the CMSW headers into C++ modules. Unlike the first step, this is not completed yet. We're about 60% done. More on the next slide on the stuff. Then we want to teach rootcling to produce C++ modules. This is necessary because we have certain I/O information that we need to add. So we can't just use vanilla C++ modules. Yeah, this is mostly done. Again, more on the next slides. Then we want to teach a root interpreter to actually load the modules instead of parsing the headers. So we have a prototype here. And yeah, then we want to compile the modules for CMSW actually with root cling, because step 2 is just with Clang, and here we actually want to use root cling, which is not ready yet. And then we actually want to use them during runtime. But yeah, so far we're not yet. We're still stuck at root cling at the moment. Okay, so let's look at step 1, or step 2. So 1, I just skipped 1 because it's already done. So we want to compile all the headers in CMSW into C++ modules. So we just use Clang and struct them to build the modules for all headers. And this is currently our progress. So we have 1,300 modules in CMSW. This is everything we have, even probably unused modules. And of those, we currently compile around 800 into working modules. The remaining 500 don't compile yet, mostly because either they have a problem in one of the headers. There are certain things that modules can't handle. Like, for example, you have a header that is not standalone. We can parse a header that is not standalone. If you use std vector and you don't include vector, then we don't know what to serialize, what declaration you actually have there. So in this case, you need to add a missing includes, and this hasn't happened yet for all modules. So for the remaining 500, we either need to add missing includes or we need to fix the dependencies. Because if the dependency doesn't compile, then they also don't compile a certain module. So the thing is, the progress is a bit hard to estimate because it's entirely possible that we just need to add 10 includes and then the rest compiles, or we actually need to fix 500 modules. But the current progress is 800 of 1,300. So we got those to compile with around 130 pull requests to CMSW. The diff is around 2,000 lines. Most of the stuff that I did there to CMSW headers is mostly just fixing missing includes. There was some broken code that the compiler didn't see so far because no one was including this header, but the modules want to compile them, so we had to fix this. And we had a few layering violations that I had to fix. And I actually think at the current point we are down to exactly 1 layering violation that I'm working on in CMSW in the whole code base. Yeah. And all the code we fix is actually not just module work. It's things like missing includes actually bite people also. If you just have a normal build without modules, you include a header and suddenly your code starts breaking because you're missing an include, and then yeah, you need to add an include to the header, or suddenly need to include some other random header because you included something else. Yeah, and if you want to follow what those 130 pull requests are and what the future comes, there's like a tracking issue where I reference all of them. Okay, then we also made 3 patches to Clang. This is just to get CMSW code working. So those are patches to the Clang module system or deserialization or serialization system. I listed the revisions here. This is mostly just stuff where some module didn't compile because of some bug in Clang. And we debugged those and patched them. Yeah, and because it's really good to have performance, to have everything in modules, I also started to generate modules and the module maps for certain external libraries that CMSW is using. I think all of them are, yeah, so all of them are used by CMSW. HEP I'm actually not sure, I just did both. So in those cases, those are libraries where we also generate modules for. So they also get the performance benefit get from modules. So it doesn't matter if you actually use external libraries, it's perfectly fine to also modularize them. Yeah, and you sometimes had to patch them, like I think HEP needed a few patches to get working. Did you upstream those? Yeah, they're all upstream. Okay. Okay, so the next step is compile headers and so next step is teach root cling to produce C++ modules. So what we do so far is just we use the Clang normal modules. But the thing is with root, we actually don't just care about the code, we actually add annotations. For example, the comments have semantic information, which is usually a bit hard for C++ modules because they don't preserve the comments. So we actually need to turn them into annotations. We also need to do a few other things. So this is why we can't actually use Clang itself to produce our modules. We have to use root cling and use the root cling transformations to get all the information into the PCM. So this is why I had to start working on making root cling produce the same C++ modules that we currently produce with Clang. Yeah, so there are a few things that actually are a bit interesting now. So one of the things is that root cling actually has a dependency now. So if root cling references another module, like for example, I don't know, library A, and you're currently library B, and library B is including something from A that is in a module, then you first need to build library A, and then you can invoke root cling for library B. The reason for this is that the modules reference each other. So they don't have duplicated code in there. They're referencing each other to save space and actually to, well, this is how the modules just work. So you don't just include everything. If you have another module, you just reference it instead. And for this, we actually need to have another module built. This is why we currently have the problem that root cling has a dependency. So this may fall away in the future, but in the moment, this is a new requirement for root cling when using modules. And another thing is already mentioned, so we had to fix some race conditions and dependencies in the root build system. So you can actually make -J200, and it works now because the modules get serious problems if your dependencies are messed up and they give you warnings that you need to build their dependencies. And so we had to fix the race conditions there and the dependencies. Okay, yeah. So this limitation only acquires actually to root modules that require root IO information. So for all other modules like external libraries and stuff like this, where you don't care if you actually generate a dictionary for like HEP-MC, in this case you can just use a normal Clang way, and the Clang way is actually using file logs and stuff like this to build and take care of missing dependency on itself. So you actually don't need to have like a job that is building non-root PCMs. By the way, the term PCM is overloaded in root, so this is actually C++ modules. There are also other PCMs and root PCMs that we are not currently talking here about. Yeah, and what root cling also now needs is like a Clang module map. And a Clang module map is a mapping between a header and a certain module. And this is necessary that we, for example, know that header A is in a certain module, so we need to have this mapping between a header and the module name. So this is an example how a module map looks like. It's really simple for data formats. It just means you have a module and there's a submodule in there which is each header, and you just write the header name again, say export, and this is just what you need to do. So there's no magic here, there's no secret tricks usually for normal root modules to get this stuff working. Just list the headers in this format, and this can usually be done just by a script for you that generates this file.
Or we can even simplify it in future using umbrellas or not. Can we use umbrellas there?
But you still need to write it.
Oh yeah, okay.
Well, yeah, we can also use umbrellas. Well, whatever works, yeah. If it's already split up in directories, then yeah. So there's a shortcut in the module maps for specifying all headers in a certain directory, and this is called an umbrella. So this also works, which is just one line. Okay, so assuming we have PCMs that are built by root cling, which have IO information, we can actually start using them in the root interpreter. So the way this works is that the interpreter just checks the usual paths where we have the dictionaries, which is LD library path, Vassilev library path, and some other things. And it just looks in those paths from modules. So if you build modules and you put them in a path, then it picks them up and uses them instead of parsing the headers. So the root interpreter for this also needs a module map, and it's the same module map that you use for root cling, which is again just mapping between a header and the module needs to load. Because on the disk you just have libc.pcm and then you include, I don't know, standard IO. So you actually want to know what module standard IO is in, and this is done by the module map. Yeah, it also takes care of linking now. So if you use a certain module like, I don't know, liba, then it also automatically links liba.so for you to no longer, or it's the same as before. So auto linking still works with modules. Yeah, and right now we just load everything because it's just a prototype at the moment. The root PCMs don't work yet, so this was just for testing. So we currently just root everything, load everything that we find every module. So memory and speed is at the moment not really the thing that we actually aim for in the end. Yeah. Okay, and then the next step, and this is also the last step that I currently have in this presentation, is we actually use root cling to compile the modules for CMSW, but this time with root cling. So what we need to change in CMSW and the other experiments is that we need to set the environment variable during building, which is root_modules to 1. This may change in the future, but this is currently how it works. This activates that in root cling we start building modules. This also activates an interpreter that we start loading modules. And you can set this to debug if you want to print debug information and see if you actually use the module or if you're just using the same old code where you parse headers. Yeah, we need to have a module map for CMSW or for any other experiment. This is pretty straightforward, so we already have one which is generated by another program. We can also just make a script that generates this for you, or have this like in the root build system in there, and the root cling in there that is building the stuff for you. Yeah. And we need to have the, once we have the module map, we can actually start generating the PCMs or the C++ modules with root cling. The only thing is that Scram, the build system of CMSW, needs the mentioned dependencies between root cling and locations now. So if you use a library, then it needs to make sure that the dictionary and the PCM for this library is built before you start using root cling on the current library. So this is something that Scram has as an additional requirement when using modules. And otherwise, it doesn't change a lot. So external libraries such as build on demand, if you use Boost for the first time, then root cling will build a Boost module for you, and it doesn't care if the dependencies are wrong, or if you have no job that is building Boost explicitly for you, it will just build as a side product. This is because this is just a normal Clang code, which handles all the dependency on its own and uses file logs to synchronize. Yeah, so this is all from my side. Questions? No?
So I have a question. Can we use the same locking mechanism instead of to define away this restriction to root cling? At least for experiments that are unwilling to change or to modify the build system from modules.
Well, yeah, but this is like post-refactoring root cling material. Because right now we read exactly this root cling on location, otherwise this doesn't really work, the root transformations. So the code that is transformating the stuff is really depending on exactly the root cling arguments we pass there. So as soon as we start refactoring this out, it would work, but right now it doesn't. So this is stuff where we need to refactor root cling and make it more flexible, and then it would work, and then we can drop the dependency. This is what I wanted to hint at when I said we may drop this requirement. So this is future talk, but right now this is a hard requirement that we have. At least in the root build system, this is what we do right now.
More questions, remote? Okay.
Okay.
If not, there is nothing else in the agenda. I would like to say have a good evening or a good day, depending on the time zone, or good night. And talk to you next time.